before I get started with this, I wanted to say I learned something new. I always prided myself in knowing the number e to a large number of digits. And of course it's 2.1828, 1828. You see the 1828 is repeated. So what's the next 6 digits? Does anybody know them? A few people know them. I will give you a clue. I will give you a clue. What's that? How many degrees?
45.
How many degrees is that?
90.
How many degrees is that?
45.
That's the next 6 digits. You will never forget.
Unless you hold it upside down.
Yeah.
Could you not stand in front of the slide so we can get it on video?
Yeah, either
Oh,
sit
okay.
and run the computer.
Now, is this a slide controller?
No, that slide controller is there.
This one.
Yes.
Okay. So anyway, I was interested in the log table. That I talked about it last year some, and about the interpolation and how the interpolation is done all wrong and could be greatly improved. And so I wondered if it's possible to keep the existing interpolation scheme and make changes in the table itself. Now, you know, the logarithms in the table are actually the actual rounded down logarithms, and the values in the interpolation portion of the table are averaged over the entire row, and there's significant errors when you use those. So I was wondering if the table itself could be modified. So the log table has been around for a long time, and the standard Irish table, which is the same that we use in the California public schools, is just a little 4-digit table. It's really not much better than a slide rule when you consider the inaccuracies in it. So I was wondering if it's possible to change the table and not the interpolation method. So the question is, what is this table all about? Is it a teaching tool, or is it something that a practitioner of computing in the pre-calculator and pre-computer age might use to do actual calculations? If it's a computing tool, it turns out it's grossly defective. Okay, now here's a story. Okay, I was working on a computer, and this computer failed to control a certain function, particularly the startup of the engine. And if the engine didn't start up, the aircraft would crash. And the problem was that the engine people were specified to put out a logic signal with a certain frequency. I think it was 1 per revolution, 1 cycle per revolution of the engine, and then the computer would take that in. But at 0 RPM, the engine was putting out noise, which the computer interpreted that as, you know, hundreds or thousands of cycles. So it never turned the throttle on. And they could have fixed that with a minor software change. You know the politics. So I fixed it by changing the hardware. And of course, the airplane didn't crash. So I was wondering if, instead of trying to change the way the teachers teach the use of the table, maybe we could just change the table itself, change the hardware. And amazingly, here's what the original table looks like. That's just a little piece of it, and there's no big surprises in there. It's got all the right numbers, but maybe we could change those numbers a little bit and come up with some better results. So, okay, each row of the table stands alone, and generates 100 logarithms, and there's a total of 19 variables in there. So what I did is I looked at each one of those table entries, and I want to increment it just by one and decrement it just by one, and see if that could lead to a better table. And then I thought, well, if that's true, maybe I could do pairs of numbers, and maybe I could do triples of numbers. Okay, but how about quadruples of numbers? No, that was beyond my patience to program into Excel. And anyway, and also then once I found a better table row, then I put that back in, and I could repeat the process. In some cases, I got some additional changes. Now, I'm not claiming that, I can't guarantee that that's absolutely the best that can be done, but the very fact that I got any improvement at all just totally shocked me. As you can see, the improved histogram is the red one, and it's not a big improvement, but I was just amazed that I got any improvement at all, and that was sort of my big conclusion here. Now, if you want to see what the revised table looks like, I'm not going to show it here, because some people might be offended to learn that the logarithm of 1 is not absolutely 0. But if you want to see what the revised table looks like, it's in the paper that should be in the conference proceedings. So anyway, the tiny improvement possible doesn't come close to what you can get by changing the interpolation procedure. So see last year's paper. Okay, not so fast. Now, I heard that there's going to be some talk about percentages. Okay, and I was told not to go into this too deep. I'd like to quote from a famous citizen of Arizona, and talk about the virtues of the midpoint as a divisor when you calculate percentages. Everybody knows that if your stock goes from 100 up to 150, you take that gain of 50 and you divide it by 100, and that gives you 0.5, and you multiply that by 100, that's a gain of 50%. And if the stock goes from 150 back down to 100, what's the decline? It's 33%. Oh, wow. Why that?
The base change.
So what I'm saying is, what you really want to be doing is dividing by the midpoint. That is, when it goes up from 100 to 150, you should use 125 as a divisor, and you'll get the same answer both ways.
But that's not what percentage is divided.
Well, that's not the way you're taught in elementary school how to calculate percentage. But this is a much more logical and sensible way. And not only that, when you add percentage gains or losses, you end up with a big error. And if you use a midpoint as a divisor, you'll still have an error, but it will be much, much less. So what you would really like when you interpolate logs is a good approximation for logs that are close to 1 or close to some known log. And as you can see here, let me get my pointer out.
One here.
As you can see here, this number here, you see, I'm using the midpoint as a divisor. And it turns out this little formula is actually pretty accurate. In fact, if you have that interpolation formula available, say as a nomogram or maybe on a special purpose slide rule, you could dispense with all but the first column of the Irish logarithm table. It's accurate to four places, and one of the reasons for that is that it matches the first two let's see, next
You
one.
have a red pointer on that one too.
Yeah, it matches the first two terms of the power series, and it matches most of the third and the remaining terms. So here once again, this is the midpoint. You see, you're dividing by the midpoint, and it turns out this is a very good approximation. But if you want to get even better, you can add this term, and you're good out to 6 decimal places for the log of 1.01. And you add this term, and you're probably, I don't know, you're probably out good to maybe 10 decimal places. It's people talk about the logarithm being a slowly converging series, but this series is very rapidly converging. So it's good to go with the midpoint, and the midpoint is blessed. Now, let's see. Here's some financial problems. The mutual fund salesmen and the certified financial planners all like to use this fundamental defect in the adding and subtracting of percentages to their advantage when they claim the performance of their investment and so on. So here's some typical questions. One involves adding of percentages. You have, I can't do this. Where is it? Okay. So here you're trying to find what's your average yield. So your fund salesman will say we average 40 and minus 40 and average these numbers, and that's an average of 4% per year. So if you start with $10,000, what it's worth now? Well, not so fast, you know. And then this once again has to do with going up and down by the same amount. Turns out you need different percentages. And here's one of my favorite. The stock advisor claims, and I've seen this, 10 years ago they recommended a 10-bagger. That means it went up to 10 times its value in 10 years. So that's a gain of 900%. So that's 90% of a year. That's just insanely, the guy must be an absolute genius, so brilliant. This just doesn't happen in the real world.
Is this compound or?
Well, that's the thing. And then I went to the Off-Time Trading Academy. I'm sure you've heard their ads on the radio.
Oh, really?
Huh?
You did. I hear the ads all the time.
Yeah, I changed the name to protect the guilty.
Okay, okay.
And so this is the kind of thing you do. So this is here we're computing percent by 100 times the final value over the initial value, and that's fundamentally flawed, and you can't really change this, but the midpoint would be a big improvement. That's not the ultimate solution, of course. The ultimate solution is to use natural logs. Okay, so don't look at the formula if you're a teacher or a certified financial planner. So here's the answers now. You do it with logarithms, and you find out that the investment has actually lost money, not gained 4% a year on the average, it's lost 950. It's lost 9.5%. So it requires a growth that's different from the decline. And here, the 10-bagger, that's 90% a year. But if you look at what the actual percentage gain is, it's actually 100 times the log of 10. That's 23% a year. that's really astonishing, but not totally insane. You should be so lucky to find such a thing. So that's about it. Percentages and the use of the log table, but I'll tell you, I was just totally surprised that the log table could be improved at all just by jiggling the numbers in it. And there's lots of surprises out there. And I'd like to dedicate this talk to Elsie Hunsaker, who was my 10th grade math teacher. And when introduced to logarithms, I asked her, how were these logarithms calculated? She said, well, your table was a 4-place table condensed from a much larger table that was computed by the government. I said, but how did they compute it? And her answer was, be quiet or I'll send you to the principal's office. Now later I found out, of course, that the computation of that government table was a major event in feminist history. And if you look in the Handbook of Mathematical Functions, and the chapter on Matthew functions, you'll find that it's written by a lady named Gertrude Blanche. And she was the first woman to lead a large government technical program. And a very interesting character. In the 1950s, she was at UCLA and the Computing Institute, but there was certain work she could not do because she could not get a security clearance. Why not? The FBI said she lived with her sister for many years. Her sister was a known card-carrying communist. That was reason number one. Reason number two is also very curious. The FBI also pointed out that she never married or had children. Yeah, and she was not a Catholic nun. So I went to UCLA library. They have a special library just for that particular topic, and I wasn't able to get any help there to find out if she was or wasn't. But it's an interesting thing. I mean, if you read her stuff in the Handbook of Mathematical Functions, you find out, I mean, she really knew her math, you know? So who cares?
Was that number 55 you're talking about?
Yeah, AMS 55. So that's all I have.
Okay.
And I don't want anybody to forget the value of E to what is it, 15 decimal places now.
459045.
Yeah, 45, 90, 45.
Just ask.
The 1820 is 2.7, 1828 repeated, 45, 90, 45. You'll never forget it.
I guess I got it, yeah.
Question.
Question?
Oh, yes, Roger.
Are these effective percentages that you got, are they the equivalent of assuming it's compounded continuously?
Yes.
Yeah.
Yes, he wants to know if the percentages computed with logarithms are equivalent to compounding continuously. And yes, because logarithms, after all, are an integral. And yeah, that's continuous compounding. And that's what makes all different time periods and all different percentages addable.
Yeah, I had some fun with compounded daily, and I tried to see if there's any significant error.
If you compound daily, you will be.
I figured the error.
You know the limit of epsilon as epsilon goes to 0. That's how close you're going to be if you compound daily.
Epsilon's 1/3.
You might be off in the 14th decimal place.
I figured it'd be insignificant, so
Yeah.
Yeah.
it was much easier to use the law. If you wanted to find the percent, then it was much easier to use the law.
Okay.
Thank you, Richard. I